So you guys aren't sick of me yet. So I guess we'll talk about complex path following and force control, and more specifically, how to do it with a robot. As always, here's the agenda. We're going to break it down a little bit. Rather than dive into the whole thing, we're going to talk about force control first, and then path control first. And then kind of combine the two, talk about what it takes to do it with the robot, do some application examples, or just videos of basically applications being done, and then the key takeaways from the overall presentation. So force control, it's pretty cool to say, force control, but it's a little more technical than that. Force control, really you're controlling torque at the same time, right? At its core, it's detecting changes in the magnitude of forces, or keeping it within a certain band, right? Applying, monitoring, and maintaining a constant force in one or more degrees of freedom, right? So it's not necessarily just pushing straight down, but you could push straight down and apply a torque as you move in any particular direction, right? Here's some common everyday examples. People, again, kind of like bin picking, people are really, really good at this. Without even thinking about it, you can very finely control how much force you output in almost unlimited degrees of freedom. So if you're starting a nail, right, in a piece of wood, you can't wail on it, but you have to have enough force to actually do anything, right? Rubbing your eyes is probably something people don't think about, but you can't jam your fingers in your eyes, but, you know, just barely brushing doesn't do anything. Anyone ever reach behind a nightstand or a piece of furniture to plug something in? That's pretty complex force control, right? First you gotta find the outlet, and then, you know, orient your plug the right way, and then push it in until it seats. Erasing, right? Too little or too much force doesn't give you what you want. We don't think about these things, we just kind of do it automatically. Robots, you gotta get a little more detailed, right? What kind of robotic applications use force control? A lot of them. Assembly, obviously, material removal, grinding, deburring, polishing, buffing. Cobots are a really good example of robots that benefit from force control. They already kind of monitor the TCP force. With a force sensor, you can do a lot more flexible tasks. Collision detection, obviously. Sometimes you don't need to exactly fixture your parts. You can kind of partially put them in an area, and you can use a 2D camera, or one thing we're doing over there is we're just touching off on two edges of the part. That gives us this corner, and we know where the part is, right? So you can use collision detection for robotic tasks. QC, we'll talk more about that in an example. That's super, super broad. Packaging, medical, surgery is very dependent on force control, right? If you're doing something inside the human body, you're going to want to monitor your forces. Physical therapy, medicine delivery, a ton of applications for force control. Some of the key concepts, you guys probably know this already, but the resolution of a force sensor is the smallest increment picked up by a sensor. The noise should be a fraction of your resolution, right? But basically, this is just how much electrical noise do you have. If you get a digital force sensor, you don't really need to worry about noise. Drift, something that doesn't really come up that often, but basically, if you've got a control force and you're keeping it there, that reading can change over time, right? Super robust sensors have less drift. If you frequently calibrate your sensor, you're going to reduce that drift. I haven't, maybe Grady has, I haven't personally seen an example of force sensor drift caused by just a long force control time period. Output rate, you guys at Georgia Tech might run into this might be more of a consideration for you guys, because you guys are doing some bleeding edge research. But for most commercial applications, the rotating force sensor is 100 hertz. You don't really need to go much more into depth than that for most applications. The exception is if your control system, I say VW, because this used to say bandwidth. If your control system rate, or your loop rate, is much higher than your sensor refresh rate, you're going to have some weirdness. It's not going to be as accurate as you expect all the time. I'll qualify this entire slide with a little text box. Unless you're doing really sophisticated, fine force control applications of like really small fractions of a newton, you probably don't need to go any further than the resolution. Just buy a force sensor. Your main consideration is going to be how does it interact with the robot, how can you actually control the forces and use the robot to react based on the forces. So that's a little bit about force control. Path following, staying on track. I tried to pick some relevant pictures for all these things. It's exactly what it sounds like. So the difference is with a robot, you define point A and then point B, and then you tell the robot to go from point A to point B. What happens in between those points, it's predictable, but you don't control it, right? So if you tell the robot to move from point A to point B, the trajectory it follows is going to be the same every single time, but you don't determine the trajectory, the robot does. So if you need to follow a specific path, you need that path following capability. Some of the typical examples might be that wire loop game. You guys ever played that at like the state fair or something? That's very fine path control that people tend to be really good at. Self-driving cars, obviously. That game that I've never been good at. If anyone's gotten past like the second hole on that thing, you're way better than I've ever played. Again, what applications use path following? A lot. All the material removal options probably do. Dispensing, especially. So, like if you look at laying down liquid gasket around a mating surface, you got to follow a path, right? Because usually you're going around through holes and things like that. Assembly, inserting a gasket. If you're folding something, that's more than just 2 waypoints, right? You probably got to go up and over or follow a specific path. Quality control, bead inspection, part scanning, probably more than just waypoints. And again, physical therapy, surgery, super dependent on paths. Key concepts of path following. These are a little less technical than the force ones. Hand guiding. So, say this is. I don't really have a good example for this. You have a force sensor on the end of the robot, and you have some kind of tool below the force sensor, right? Hand guiding is where you grab the actual tool and move it with your hands. So what the force sensor does is it detects what forces you're putting on the tool, and it commands the robot to move along with you. So your force sensor is reading what you want the robot to do, and assists you by commanding the robot. The path, pretty self-explanatory. It's whatever trajectory is followed by the tool center point of the robot. The TCP, that's important. It's usually made up of thousands of waypoints. So if you use one of these force sensors and record a path by hand guiding, and then you open up the program as a script file, you're going to see a ton of different waypoints, right? So what path recording is actually doing is easing that process of making thousands of waypoints. A control force, I think I mentioned this earlier, but it's a constant force, right? So if I need to move from point A to point B, but I need to make sure I'm putting 5 newtons downwards the whole way, that 5 newtons is a control force. And then a process move is following a path, but making sure your speed is constant throughout all of it, or at least controlled in some way. And especially for like a dispense application or something, you want to make sure you're dispensing, your dispense feed rate is probably not going to change for most dispense applications. So you want to make sure your accelerations, decelerations, all that is accounted for and very tightly controlled during that dispense move. So that's what a process move is. So putting the two together. I used a fountain pen as a picture of this because I think that's a pretty good example of how people do very complex path and force control at the same time without even thinking about it, right? So it's different with a ballpoint. The ballpoint uses like a control force. A fountain pen would use a variable. Your control force is always changing, depending on if you're moving up or down. That's anyway. So the challenges with doing this, when you program from a pen bit, it's generally done with waypoints, right? You guys programmed robots, URs before. You're putting in waypoints and telling the robot to move to a particular waypoint. Even if you have a circle or a curved surface, if it's a constant radius, not a big deal, right? You just use a circle move, that's it. If you've got a variable radius curve, it gets pretty tough to do that with just waypoints, right? I've got to connect the dots picture up there. Until you kind of know what the final picture looks like, it's very tough to just go from dot to dot to dot, right? Whereas if you knew you were tracing an airplane, you could just tie all that stuff together. You're not working with waypoints at that point. So working with a robot is kind of like a connect the dots where you have no idea what the final picture actually looks like, because you're just dealing with each discrete step. It gets not only very tedious, but tough to debug when you're done with it. It gets even more complicated if you need to change the angle of your tool all over the place. This is something that, again, humans are really good at. A lot of path following and force control elements, right? If you told me I had to sand, some crazy complicated part, I could probably do it. I could probably get pretty close on my first try without thinking about it, because we're just good at it. Being good at that skill doesn't necessarily translate to programming a robot, right? So if I had to program a robot to go polish Honda Accord or something, right? It would be a nightmare to determine exactly what angle the tool needed to be at every point along this, not just a path, but a surface, right? So those are the two biggest challenges. Now, solutions to this, you could program your waypoints manually. The big pro is that you don't need a force sensor or any other convoluted software, but you will hate doing it the whole time. You're going to hate programming the waypoints when you need to change something. Trust me, you're going to regret it. So the other solution is path recording with a force torque sensor. This is probably the first step towards getting more sophisticated with it. Like I said, you can use the force torque sensor and the hand guiding function to record a path. You can execute it at the recorded speed, at a constant speed, or even relative to an offset. Recorded speed is kind of cool. It's a little uncanny because when you play back what path you record, it looked kind of like a ghost of you guiding the robot. Like it really moves that tool center point exactly like you moved it, with all your pauses and all your motions. Constant speed is, if you trace this path, but it wasn't perfectly, you didn't maintain a constant speed. You're just recording the positional data along that path. Constant speed means the robot will play it back at a constant speed regardless. And relative to an offset is if, let's say that example of recording a path, now your part isn't fixtured down perfectly every time. You can use a camera to locate some kind of origin feature of that part and trace your path from there. This is Roboteek's path recording video. They've got a pretty decent path recording example of what that hand guiding path recording process is like. So you'll notice it's staying underneath the voice sensor, right? So for those of you that work with law but not necessarily the voice sensor, you know what free drive is? It's that it releases the servos and guide the robot. That's not what this is, right? In free drive, you're actually manipulating the robot. With hand guiding, the force sensor is commanding to the robot. Technically, the forces that you're putting on the tool on the robot. Does that make sense? I haven't paused for questions today. Does anyone have any questions so far? So, if you have something a little more complex than this, where you can't necessarily reliably hand guide a pointer to teach the robot, I think I've mentioned Artemines before with their monitoring package. So this is really what Artemines does. They do offline robot programming. So here, for more complex parts, That's not a more complex part, but it's the only screenshot I could find that shows this CAD to path thing. You can actually import a step file of a part, right? So say your path needed to be exactly along the edge of that. You could import the CAD file into Artimize and pick edges to generate a path for the robot, or one of the examples we should see later on is if you have a path that's just independent of the part itself, right? So the example is polishing a muffler, and you want it to follow kind of a swirly path just so it covers the entire surface. You can take that and project it onto a part and account for all the curvature. You can orient the TCP however you want. I don't remember if this is a video, but this really unlocks a lot of path following capability from the robot without you having to physically program waypoints. So, things to consider when you're deploying or when you're application considerations. Just stop that one bit. So a force sensor, you can detect forces. It is not a safety rated device. Okay? So you should not, the safety of your system should not depend on the force sensor detecting anything to do with a human. It is not a safety rated device. How I've seen it, a force sensor can be used in surgery just because it gives you that fine force sensing resolution, but they have thoroughly evaluated the entire system, right? So this is a subtle thing. I don't think anyone would assume that a force sensor is a safety rated device, but I thought that's something important just to throw up there. You can use it as a soft safety device, right? So you can say the force sensor detects some lower threshold of force than my safety system and stop there. But the safety rated system is on the robot. Force sensors are not safety rated. So do not make them the last line of defense when you need to stop the robot. Jigs and fixtures, like I said before, they're the most reliable, they're the simplest, they might be the cheapest, but they're not necessarily always feasible or the most efficient. You can use a 2D camera or a force sensor, mention both of those, to locate a part and offset your path based on where you find the part. Here's a video kind of demonstrating optically with the Robotique camera. So that's the path that it traces. And this is just a mock-up of the process. This isn't an application, it's just showing functionality. Right? So it's still tracing the same path, but your part, you don't need to fixture your part at that point. You can just have it on a table. What's the reach and the pose required of the robot? This is always going to come up, right? Especially if you're doing some kind of dynamic part location. Make sure your robot can actually reach all the points of your path with your tool oriented properly. Or you could unexpectedly run into a singularity. This is important. Does everyone know what a singularity is? Or a singular position? You will innately know what a singularity is the first time you ever program a robot. You will run into one. I wasn't a math major, so I don't know the exact kinematic definition. The kinematic definition doesn't make sense to most people anyway. It's basically when you have multiple solutions. So like imagine if your elbow could bend both ways, right? And you're holding something in your hand and you need to move it straight back, right? So with your elbow fully extended, if you need to move that part straight back, your elbow could bend that way or that way, right? There's more to it than that, but essentially a fully outstretched position like this robot right here, how do you tell the tool center point to move straight down in a line? It's going to error out if you try to move it vertically down, right? That's what a singularity is. There's other examples. Sometimes your joints line up in a certain way, and what needs to happen is if you tell it to move in one direction, it needs to flip around to keep going. Once you've kind of seen some singularities, you know what to expect them, because you will run into them at some point in almost every application. Speed control, not only speed but also force control suffer in singular positions or near singular positions. That's why if you're hitting a singularity that you're passing through instead of like at the end of reach, you'll notice your joint speed just kind of goes crazy. It speeds up until it flips over and then it resumes. So your speed and force control get weird near singularity, so keep an eye out for it. The complexity of your surfaces and edges, the more complex it is, the more time you're going to spend getting everything perfect, right? Having that CAD model system helps a lot. You can also kind of use control forces to dynamically adjust to a surface. This is a demonstration. This wasn't what we're looking at. This is only with the force sensor. This is actually an ATI force sensor. They're using that force control to follow the surface. End of arm tooling factors, we make sure force sensor, right? Software works in slightly different ways. Different force sensors use different mechanisms to detect forces. Some of them use strain gauges, some of them use a rubber dome and just detect the deflection in the dome. There's different ways to sense force and control a robot with it. So keep that in mind. If you're doing a dispense application, who makes your dispenser, right? What are you dispensing? At what rate are you dispensing? If you have a, your research guy, what's the opposite of viscous? Just thin? Inviscous. Perfect. So if you need to dispense water at a milliliter a second, that's a little bit harder than dispensing maple syrup at a milliliter per second, right? Just because water wants to run, you got to monitor it much more closely. How does that affect your, or how does that interact with your robot control loops? You just got to take account of all the components in your system. What are you cutting with? How forgiving is your process for cutting or grinding or polishing or deburring? What's your part made out of? What's your desired finish? If you need optical glass, that's different from polishing something made out of wood, right? So all sorts. There's too many considerations really for your end of arm to summarize in a PowerPoint slide. So we'll just leave it at that for now. Examples of applications. So here's one we did. Well, that thing happened again. We're about to have the longest 30 seconds. That generally happens. So basically what this is a complex surface, right? This is a ATI polishing head. It's pneumatically driven. We've got a buffing wheel. We're basically just buffing the surface of this high gloss veneer. That is not a constant radius curve, right? So we're using kind of elements of all of it, path following. This isn't a super complex surface, it's just kind of tedious to program a bunch of waveforms. And we're using a force sensor just to get feedback on the, oh my goodness. But basically what he's doing there is he's taking a path, right? He has this CAD model of the muffler. He took a spiral path, projected it onto a curved surface, and now he's setting his tool orientations, simulating what the tool's going to look like. So for polishing, you always want your tool to be normal to that surface, right? And with a control force, pushing normal to the surface. So in just a couple of minutes, he was able to generate a robot path and all the control forces, or at least the tool orientation, so that he can say, apply control force. And so now once you generate the program with Artemines, you push it out to your robot and let it actually run. Ultrasonic inspection. So the control force is very important here, and this rim, you can see it's one of those fancy ones. So not only do they have to maintain certain tool orientations or adjust the orientation as it moves, they have to stay on a path, apply control force, and orient the tool along the whole thing. So this is a run through of how they use Artemines to quickly do all of that. I think in this particular example, he just picked an edge off the model instead of needing a separate path. Yeah, so that's that particular example. I couldn't find a video of this, so I just made an animation. But this is basically that concept I said about locating the corner of a part. Basically what's going on here, this is a big stainless steel plate. You're just finding the corner you're finding the corner by touching off on those two edges, and then generating this path can be done from the robot pendant. Waypoints, again, would be a little tedious. This is easy enough to do with scripting. So, just a little concept there. So key takeaways from all this: sensitive force control tasks, insertion, assembly, there's no limit to what they are. They might require a force torque sensor. Something I didn't mention, the UR is a force sensing robot, right? It can detect forces at the tool center point within a window of 20 newtons, plus or minus 10, right? For insertion, assembly, all that kind of stuff, most likely that's not fine enough. A force torque control sensor allows control over not only the forces, but gives you more control over path of the tool center point, and using software such as Artemines makes those complex path-related applications much simpler, and also means you're up and running quicker as well. Thank you guys. That was a long day of presentations, I'm sure. Any questions?